Let's go through these derivatives really quickly. For the first one, there's nothing to rewrite. Each piece is already in a super nice form for me. So when I take the derivative of that first one, oh, by the way, I've been seeing there are a couple different notations for taking derivatives. I like to use the F prime. It's just kind of a convenient notation. We see it a lot, but I could also write df dx, and that would mean the same thing. They would both mean take a derivative. This one, I'm just using our power rule. So I'm going to take 10 times 3. I'm going to do that 30, subtract 1 from the exponent. There's no work to show. You don't have to show doing 3 times 10. You don't have to show in that exponent doing 10 minus 1. The more of that you can kind of get faster with the arithmetic in your head, the faster the problems go. So I'm going to have -4 times -5, a positive 20. And when we subtract 1 from the exponent, we just want to be careful that -5 minus 1 gives me -6. There is no way around it for cosine. You just have to memorize the trig derivatives. The derivative of cosine is negative sine of x. Now for my next problem, I personally would rewrite both of these. It's totally fine to treat that as a quotient rule or to treat that as a quotient rule, but it's going to be more time consuming than doing the stuff from section 2.2 of our book, where we practice rewriting the fractions and the exponents. There's nothing wrong with doing quotient rule, but neither of these require quotient rule. That 2 over x squared, I can rewrite as 2 times x to the -2. X cubed divided by 5. Dividing by 5 is the same as multiplying by 1/5. So I would write that as 1/5 x cubed. So I haven't taken a derivative yet. All I've done is rewrite the function. By rewriting it, I've saved myself from chain rule and I can just use the power rule. If you did it, I mean, I can save myself from quotient rule. If you did it with quotient rule, that's totally fine. You should get the same answer in the end. It just might not look exactly the same. But it's a lot faster for most students to just go ahead and use the power rule. Now the last one, I for sure am going to have to rewrite those because I don't have any other way to deal with a cube root. So here I'm using those pre-calculus skills to rewrite this function to say the cube root is the same as having something to the 1/3 power. And since it's squared first, this function, oh, you know, I was going to say a typo. This is my derivative over here. I'm going back to make sure I put that notation in. Here, I'm not taking a derivative. I'm just rewriting the function. That's x to the 2/3. The square root of x is x to the 1/2 power. Because it's in the denominator, I can write that as 5x to the -1/2. And this last piece is already the way I want it, so I'm going to leave it alone. Another thing that I've been noticing just in office hours is if you have addition and subtraction between parts, you can really think about each of those pieces on its own and do what's right for each individual piece that's separated by addition or subtraction. So I'm going to separately look at the x to the 2/3 and then separately look at the 5x to the -1/2 and separately look at the 4x to the -3. So taking all those derivatives, I am looking at 2/3 x. I'm pretty quick with fractions in my head. If you're not quick with fractions in your head, this is the one place where I will say, if you're worried about it on the test, just write that as 2/3 minus 1 and move on with your life. Right? Like maybe go back and simplify that if you can later. If not, don't worry about it. I'm quick with the fractions in my head. Oops, I almost lost my -1/2. So I'm going to know that that's -3/2 minus a minus is going to make that a plus 12x to the -4. I'm going to pause there. I'm not seeing questions in the chat, but I'm pausing for a second just in case, one, I've made a mistake and someone needs to correct me, or if someone has a question for any part of this. I do not know how loud that sound is next door, but it's pretty loud over here, given that there's a wall between us. Oh, the coefficient is 12. Yes, thank you. See, I told you, I make mistakes. That's why I paused. Thanks. I think maybe that's it. So the two things that I for sure want to talk about today are chain rule and some practice with more trig. Are there other things anyone would like to add to my list of stuff to talk about? Yeah. Oh, for velocity stuff? Sure. Yeah. Okay. Multiple derivatives. So I'm gonna label that as like vocabulary or rates of change problems. Because none of what you're doing on those is different. It's really just the vocabulary part of it that is telling us what to do. Okay, I'm not sure where to start. I think I'm going to start with chain rule. I'm going to write some stuff that is going to look really gross. It's going to be nonsense, and I'm going to write it fast. Don't try to take notes on this. I really love to do this on a chalkboard. It's really satisfying on a chalkboard, but don't have a chalkboard in here, so I'm going to use pens. Hopefully I can make it as satisfying. The first thing that I want to do really quick is, I might have told you all this, but the way that I remember the product rule is to say to myself, I've got two things that are multiplied together. Since there are two letters there, two things, I'm going to write it twice. So I write FG, I write FG. I've got addition, and what usually goes with, sorry, I gave away the answer. I've got multiplication. What usually goes with multiplication? Yeah, and then I chase down the derivative. Now, the cool thing for me about remembering it that way is that it also works if I have three functions multiplied together. So if I have three things multiplied together, then I write FGH, FGH, FG is 3 times. What goes with multiplication? Addition, and then I chase down the derivative. Okay, someone pick a number between 5 and 10. 7. So it's going to be a stretch for me to squeeze this in here, but I'm going to put 7 things multiplied together. Okay, I got 7 of them. And then I'm going to take the derivative. Since I got 7 of them, I got to write them 7 times. One, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. See, I've learned over the years, the F's are the fastest and most compact letter for me to do that with. It's kind of awesome. So I've got multiplication between all these things, which means I need addition everywhere in here. And then I'm going to come in and chase down the derivative. Pretty cool, huh? Now, I got 7 of these things. And each of those 7 things has exactly one f prime in it. So I'm going to factor that f prime out. But if I pull the f prime out of here, I should have 1, 2, 3, 4, 5, 6 regular f's. But if I have f times f times f times f times f times f, what's the shortcut way of writing that? Yeah, so we'll write it to the power. I'll write that as f to the power of 6. Well, from here, if I pull that f prime out, I have another f to the power of 6. And I'm going to pull the f prime out and have another f to the power of 6, and another one, and another one, and another one, and another one. Oh, did I have too many? No, I'm good, I'm good. Okay, so how many of those f to the 6s do I have? 1, 2, 3, 4, 5, 6, 7. So I've got f prime and then 7 of those f to the 6s. Now I didn't let you in on this little secret, but over here on the left-hand side, that was an f times 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 an f, which I could also write as a power, which means I started with f to the 7th, and then I took its derivative. Now, more traditionally, we'd probably write that as 7f to the 6th times f prime. Chain rule is secretly product rule on steroids. So that's not worth putting in your notes. Here's the part that is. I'm not going to write out all the f's again. But if I had some function raised to the 50th power, and I went to take the derivative, then we can imagine what was going to happen with all those f's and f primes. Oh, okay. I've somehow gotten into a menu that what if I just keep pushing the button? No, it's not helpful. It's like telling me to push something to return. Okay. Sorry. Okay, I think I got this figured out. Okay, cool. So you can imagine that I've got 50 of those f's multiplied together, so I'd write them all out, I'd write it 50 times, I'd chase down the derivative, I'd factor the f prime out. But the thrilling conclusion is I'd end up with 50 of those regular f's to the 49th power times f prime. So if I had something like y is equal to 4x cubed plus 12x, whole thing to the 13th power, and I wanted to take that derivative, then all of that stuff inside is acting like that f for me. So I'd have kind of follow that same rule, take that coefficient, bring it down, sorry, take the exponent, bring it down as the coefficient, and have all that stuff raised to the 12th power times, and this is the extra piece. This piece on the back here is my chain rule piece. We're going to multiply by the derivative of the inside function. So when I take that derivative of 14x cubed plus 12, sorry, 4x cubed plus 12, I get 12x squared plus 12. If I had y equals cosine to the fourth x. This is secretly a chain rule thing, because I'm going to need to rewrite that to think about it as cosine of x whole thing to the fourth power. And when I take that derivative, it's like my function here is cosine x. So I'm going to have 4 times that function thing of the cosine x to the third power times, and that piece on the back, I'm taking the derivative of this inside function. And the derivative of cosine is negative sine. Questions? Oh yeah, totally. So, sorry. So if we switched up this problem and made it look almost the same, but instead this said y equals cosine, and I put the 4 on the other side of the x, this means that we have cosine of x to the fourth. But when I take the derivative here, it's a little bit less obvious that that same rule is going to apply. I don't have like a power to bring down in front. So we're going to think about that chain rule like I'm peeling off layers. So that outside layer is the cosine. So I'm going to start by taking the derivative of the cosine, which would give me negative sine. And then the chain rule piece is going to be that I'm going to take that inside part and multiply by the derivative. And it's that magic of multiplying by the derivative of sort of that inside function that is really at the heart of our chain rule. So these two problems, although they looked very similar, have completely different answers. And you better believe if this was a multiple choice test, I'd write both of those on there. But luckily, you're not taking multiple choice tests. Not for calculus anyway. More practice. So one of the questions that I get a lot is like, how do we know when to use chain rule? And my answer is you can always use chain rule. 100% of the time you can use chain rule. But I think you're going to confuse yourself if you do that. But let me show you what I mean. So let's say that I had, I've been using cosine. Let's switch it up. Let me just make this a sine. If I went to take the derivative here, I could technically think about this as saying sine of a function. So I'd go, okay, what's the derivative of sine? Cosine. I'd keep my function the same and then take the derivative of the inside. But what's the derivative of x? Right. So if kind of that inside function is just an x, we don't really need to do chain rule. And in fact, I think you probably shouldn't, because I think you're more likely to confuse yourself with that one. But if what's inside is something slightly more interesting, even just ever so slightly more interesting, like sine of 3x, this does require chain rule. So now when I take the derivative, I go, oh, well, sine is that outside function. Derivative of sine is cosine. And then I'm going to multiply by the derivative of that inside function. And the derivative of 3x is 3. I will also say that just to be confusing, 100% the book is going to rate this as 3 cosine 3x. They're the same. It doesn't matter where you put that times 3, but for sure the book is putting it in front. Okay, are we ready for some gross chain rule problems? Because there are some gross ones on that practice midterm, let me tell you. Okay. Common times that we're going to be forced to use chain rule, whenever we have roots with stuff inside of them that isn't just x. So if I had f of x is equal to the square root of 3x squared minus 4x, I won't make it too terrible. And I need to find the derivative. My first step here is going to be to rewrite it. But because I have, in this case, subtraction, but addition or subtraction inside of the root means I can't separate this out. If this had been multiplication, then I could take the roots separately. But with addition or subtraction in there, I have to keep it all as one piece. So when I rewrite that, that's really 3x squared minus 4x raised to the 1/2 power. Again, that's like my rewriting step. Haven't taken a derivative yet. Now I can come in and take a derivative. And I've got some stuff to the 1/2 power. So my derivative is going to look like 1/2 times that stuff to the negative 1/2 power times the derivative of the stuff. (6x minus 4). Do we have to simplify that? Generally, no. If you wanted to simplify that, in this case, it does look like I could take that 1/2 and instead of, I wouldn't try to distribute it here, but I could distribute it to the 6x minus 4, like if you really wanted to do something. But personally, I would just walk away. Okay, overall structure, I have some stuff raised to the 5th power. So I know that I'm going to end up with 5 times that stuff to the 4th power. Then I'm going to have that chain rule part that says, oh, I need to take the derivative of what's on the inside. But what's on the inside is a quotient rule. So I've got that sine x over x cubed. But out here, I'm going to have to do quotient rule on that. So the derivative of sine is cosine. Then I'd have times leaving the x cubed alone, minus leave the sine of x alone, times the derivative of x cubed, all over that x cubed squared. There are alternatives to doing it that way. One possible alternative would be to look at that original function and instead to say, oh, I can like distribute that 5th power. So that could be sine of x to the 5th power divided by x cubed to the 5th power. And I could rewrite that as sine of x to the 5th times x to the negative 15th. I don't know that that's necessarily any better. But if I had done it that way, now I'm looking at a product rule. Should we do it this other way too, just for fun? So if I do the derivative this way, then in terms of that product rule, I can kind of see this whole thing as my f, see this whole other thing as my g, so that I've got like an f times g going on. Well, the derivative of sine of x to the 5th has a chain rule within it because I've got something raised to the 5th power. So I get 5 times that sine of x to the 4th times cosine x. Then I would multiply that by leaving the g alone. So x to the negative 15th plus I would leave the sine of x to the 5th alone and then multiply by the derivative of g. So negative 15 x to the negative 16. I'm going to argue those two don't look anything alike. And I don't think it's worth our time necessarily to show that they are, but I will just hint at it for a second here. So if you look at this, if I think about kind of distributing this through, looking at the numerator, that's a sine of x to the 4th times a cosine. So that's a 5 sine x to the 4th times a cosine. And yeah, we'd have to deal with some exponent junk. And then over here, I'd have a sine x to the 4th times another sine, which would become a sine x to the 5th. Right? And there I'd have a 5 times a negative 3, and that'd give me that negative 15. So I promise there is algebra you can do to make those the same, even if it's gross to get there. Questions about this? Okay. So I'm going to show you a few, just a few more trig derivatives because they're ones that kind of look friendly, but often mistakes are made on them. But the first thing we're going to do, because we've only been using sine and cosine so far, is to make sure that we've got all 6 trig derivatives memorized. So I'm just going to list them out. You can quiz yourself, list them out on your own paper. Sine of x, cosine x, tangent x. You can just, now obviously you can write all of these down on your note card. But every time you look something up is time that you don't have to be thinking through another problem. So the more of it that you have kind of memorized, even if it's just through repetition of doing problems, the better. The derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. Derivative of tangent of x is secant squared x. The derivative of secant of x is secant of x times tangent of x. derivative of cosecant of x is negative cosecant of x cotangent of x, and the derivative of cotangent of x is negative cosecant squared x. Okay, that was like 6 mouthfuls, but there's our list that we have to work with here. So here are some of the common trig things that sort of get people into trouble that look pretty simple. The first one is just, we kind of already did one with the difference in notation, but if I have y equals tangent cubed x, recognizing that the 3 on this side, the 3 like being closer to the tangent part, means that we should take a second to rewrite that as tangent of x cubed before we apply that chain rule. To make that 3 times tangent of x squared times secant squared x. Other deceptively nice ones. Somehow when we just have numbers, those feel harder somehow. So if I had secant of 5x, when I go to take the derivative, that like outside function is the secant part. So I'm saying, okay, what's the derivative of secant of something? It's secant of that something times tangent of that something times, and then here's the chain rule part. I need to multiply by 5 because it's the derivative of that inside function. The number one mistake that I see made on this problem specifically with secant is calculus can never change the argument of a trig function. There is no derivative or antiderivative or limit you can take that changes what's inside of the trig function. Only trig identities can do that. So if I took the derivative of secant of 5x, that means that derivative is secant of 5x times tangent of 5x, not secant x tangent x. But that's like one of the number one places that people make mistakes. I would say these are the 2 primary ones, like recognizing that notation wise, that 3 next to the tangent, not after the x, means that the whole thing is cubed. And remembering to keep the same thing inside of the trig function when we take derivatives.